I'm glad you're here tonight, because we're about to drift into something that has puzzled scientists, thinkers, and pretty much anyone who has ever stared at the night sky and wondered how all of this holds together. You've probably heard the word space-time 1,000 times, maybe in documentaries where the narrator speaks in that low hypnotic voice, maybe in books that try to explain it with grid diagrams that somehow made things more confusing, or maybe in conversations where someone confidently said they understood it and you had the sneaking suspicion they were guessing. It's one of those ideas that seems simple when you first hear it, but then the edges of it start stretching and curving until you feel like you're holding onto mist. And that's what makes it strangely comforting to talk about right before sleep. There's no pressure to solve it, only to wander through it slowly and let it unfold at its own pace. Before we sink into this, I'd love to know something small and personal, something grounding. Where are you listening from tonight? And what time does your clock say right now? It's funny how we're about to explore something that's supposed to weave the entire universe together, yet each of us arrives here from our own tiny corner of it. Some of us are settling into bed, some are halfway through a long night shift, and some are just taking a moment to unwind before giving sleep another try. Wherever you are, I'm glad you decided to join this little nighttime detour, and if you find these soft science wanderings helpful or soothing, or simply a nice companion for drifting off, it would mean a lot if you'd like the video or subscribe. It helps this gentle corner of the internet reach others who might need something quiet and steady to fall asleep to, but only if it feels right. For now, let's take a slow step into the question that brought us here. Why don't we understand space-time yet? Something that seems like it should be straightforward, because space is where everything goes and time is when everything happens, so when you put those together it ought to make sense. Except it doesn't. Not quite. Not fully. Not in a way that lets us say, yes, we've got this, the universe is tidy and cooperative. And maybe the reason the answer slips through our fingers is because we're still trying to wrap our minds around something that isn't shaped the way our minds expect. There's a moment that happens to most people the first time they hear the word space-time. It's a slight pause, as though the brain is trying to decide whether it's dealing with a math problem, a science fiction idea, or a philosophical puzzle. We grow up thinking of space as a vast emptiness, a backdrop, the place where stars hang and galaxies spin, and we think of time as a sequence, a flow, the hours ticking past. They feel separate because that's how we experience them. We stand in one place and the clock moves forward. Simple, but then you learn that space and time are not two things but one intertwined structure, and suddenly the simple picture tilts. It's no longer a canvas with events painted onto it. It's something flexible, something that bends, something that reacts to mass and energy. And that reaction is what becomes gravity, which is already strange when you think about it. We were all taught that gravity was a force that pulls things together. But in Einstein's picture, it isn't a pull at all, it's geometry. The shape of space-time telling objects how to move, and objects telling space-time how to curve. That alone is enough to make most people blink slowly. Even people who dedicate their lives to studying physics sometimes admit that they don't understand space-time in the way we usually define understanding. They can calculate it, they can predict how it behaves, they can write equations that match what we observe in the universe, but understanding something intuitively, with the ease of saying 2 and 2 make 4, that's a different story. Space-time refuses to fit neatly into our everyday experience because it doesn't care about our everyday experience. It operates on scales far larger and far smaller than anything we interact with. So when we try to grasp it, we're trying to use tools built for life at the human scale to interpret something decidedly not designed for the human scale. Imagine you're holding a sheet of fabric. You press your fist into the middle of it, and you see the dip it creates. If you roll a small ball across it, the ball curves around the dip as though it were being pulled. That's the classic visual explanation for curved space-time. It's a nice picture. Helpful, in a way. But it's also misleading because the sheet is sitting in a larger space. Gravity in the demonstration is actually real gravity acting downward, not the simulated gravity of geometry. The image works as a metaphor, but the universe doesn't actually sit on a giant table with a giant force pulling down on it. Space-time curves in a way that's difficult to visualize because it curves through itself, not into something else. Our brains don't naturally picture dimensions beyond the 3 we move through, so even the best metaphors fall a little short. That's where things start to feel slippery. If the metaphors don't fully match reality, and the equations don't translate cleanly into pictures we can carry in our heads, then understanding becomes something more like approximating. We get close, but we don't quite get there. And maybe that's why discussing space-time feels like gently pressing into a mystery. It doesn't resist, it just keeps stretching. People often ask why the universe needs such a complicated structure in the first place. Why not simply separate space and time and keep things tidy? The truth is that nature doesn't seem particularly motivated by our desire for simplicity. The combined structure of space-time emerges naturally when you look at how light behaves, how objects move at high speeds, and how gravity influences everything. The speed of light becomes a sort of anchor. It stays the same no matter who measures it, and that stubborn speed forces space and time to adjust themselves around it. One observer might see two events happen at the same moment, while another moving at a different speed would disagree. Time becomes flexible. Distances shrink or stretch depending on relative motion, and suddenly space and time can't operate as separate concepts anymore. They merge into something unified, something that accommodates the fact that different observers can experience reality differently without contradicting the laws of physics. The moment you accept that, something else follows. If space-time adjusts itself depending on motion, then the difference between space and time is not as absolute as it seems. They can mix, they can trade roles, time can behave differently in different conditions, space can stretch, and these distortions are not just theoretical. We measure them, we rely on them. GPS satellites, for example, experience time differently because they orbit farther from Earth's gravity and move at high speeds. Without correcting for those time differences, your phone's navigation would become hopelessly inaccurate within minutes. So even though space-time might feel abstract, its effects show up in familiar ways. Yet understanding it fully still remains elusive, because the very idea that time can run differently, or that space can stretch, is not the kind of thing our senses evolved to detect. Another reason we struggle with space-time is because it sits at the intersection of two major theories that don't play nicely together. On one side, there is general relativity, Einstein's geometric masterpiece that describes planets, stars, galaxies, and the universe at large. On the other side sits quantum mechanics, which handles the tiny scale, the level of particles, probabilities, and strange behaviors that seem to follow their own rules. Both theories work astonishingly well in their respective domains. But when you try to apply both at the same time, especially in places where space-time becomes extremely curved and extremely small, like the center of a black hole or the first moments after the Big Bang, the two theories clash. The equations break, the predictions fall apart. It's as though the universe has two sets of instructions, both correct yet incompatible when they overlap. And space-time sits right at that uncomfortable boundary. This tension creates a sort of scientific limbo. We know space-time exists. We know it bends and stretches. We know it responds to mass and energy. But we do not know what it's made of, or if it's made of anything at all. Some physicists propose that space-time is smooth and continuous, like a perfect fabric. Others propose that it's granular, made of tiny discrete pieces too small to see. Some think it could be emergent, forming from something even more fundamental, something not yet discovered. In that sense, space-time might be like a mirage that appears when deeper structures interact in complex ways. Or maybe it's real in the most literal sense. We simply don't know, and that lack of certainty is part of the puzzle. Trying to understand space-time is also difficult because studying it requires experiments and observations that push technology to the extremes. It's easy to test physics in a lab when the distances are small and the forces are manageable. But when the subject of study is the structure of the entire universe, or how space bends around a black hole, the opportunities to gather data are sparse. We can't go to a black hole and measure its curvature directly. We infer things from the way stars move or from ripples in gravitational waves that travel across the cosmos. We build machines that measure tiny distortions in laser beams caused by gravitational waves passing through Earth. Those measurements tell us something about space-time, but only in the most delicate, indirect ways. It's like trying to understand the shape of a creature you've never seen by studying only the ripples it makes when it swims past you. The limits of perception, tools, and scale all contribute to the challenge. Our intuition is shaped by experiences close to home, on a planet where gravity feels constant, where time seems steady, and where distances don't usually stretch or bend. Space-time operates beyond those boundaries, so naturally it feels unfamiliar. The more we try to picture it, the more it slides away from familiar patterns. even explaining it often requires comparisons to things it is not. We call it a fabric, but it isn't cloth. We describe it as a grid, but it isn't drawn. We imagine it stretching, but stretching implies a substance in a larger space, and space-time isn't inside anything else. It is the thing everything else is inside of. That mismatch between what it is and what we can easily imagine is one of the biggest barriers to understanding it. And yet, that difficulty is part of why people keep returning to the subject with a sense of wonder. Even if you can't see space-time directly, you can feel the edges of its influence. Every falling object, every orbit, every second ticking on your watch is shaped by it. We live within it constantly, even if we don't fully grasp its nature. And as we ease further into this long exploration, we'll keep unraveling why this strange union of space and time remains just out of reach, why scientists keep searching for clearer answers, and why the very structure we live inside still surprises us no matter how closely we study it, gently moving from one idea to the next as the night settles in a little deeper. There's something quietly fascinating about thinking of the universe as being held together by something you can't touch or see, something that never makes a sound and never sits still, yet manages to shape everything from the way planets orbit to the way your feet stay on the ground. When people talk about this strange structure, they often picture some kind of invisible sheet stretched under the cosmos, something smooth and steady that lies beneath everything. But the truth isn't quite that simple, because this structure isn't truly a sheet, and it definitely isn't steady. It bends, changes, stretches, and responds to everything around it, even the smallest shift in energy or mass. And the more you try to picture it, the more it seems to slip away, as though it's not really designed for the kind of imagination we use for ordinary things. If you think about your everyday life, everything seems solid and predictable. The floor stays flat. Gravity pulls downward rather than sideways or in some unexpected direction. A ball thrown across the room follows a path that feels familiar. You don't wake up wondering whether you'll slide off the bed because Earth suddenly bent the wrong way. Things stay in place, but that sense of stability is only the surface of what's really happening. Beneath the everyday view is a world shaped by a fabric that's constantly shifting, in quiet ways we never notice. To really sense how strange this structure is, imagine holding a piece of elastic cloth between your hands. If you press your finger into it, the cloth dips. If you stretch it, the pattern changes. But if you let it go, it tries to return to its original shape. This is a common comparison people use when they first hear about how space bends around mass, yet it doesn't quite capture what's going on. The cloth has a resting shape. It has a direction in which it sits. It depends on gravity pulling down on it. None of those things apply to space-time. The comparison works only in the most loose sense, a way to get your bearings before the real strangeness sets in. Because space-time isn't a material. It isn't stretched over anything. It doesn't sit inside a larger space. It doesn't sag or droop under a hidden force. It is the very stage on which everything else exists, and that means we don't have a good everyday object to compare it to. Even the word fabric feels like it oversimplifies things. A fabric is made of threads, tiny pieces woven together. If you look close enough, you can pull it apart. Space-time, as far as we know, doesn't behave like something built from small pieces, though to be fair, we haven't been able to test it at the tiniest scales where its true nature might be hiding something more complicated. Right now, our best experiments suggest that space-time is smooth, but our theories suggest that smoothness might be an illusion, and that hidden beneath that smoothness could be something much more intricate, something that only appears smooth because we're too far away from the smallest details. That tension is part of why this structure feels so hard to understand. On large scales, it acts like a smooth continuum, allowing planets, stars, and galaxies to trace graceful paths. On small scales, the rules of quantum mechanics step in, and smoothness becomes questionable. Things begin to fluctuate, jitter, and behave in ways that no classical fabric would ever allow. This conflict feeds into one of the biggest questions in physics. What really holds everything together when you zoom in far enough? Is space-time something continuous? Or is it more like a mosaic of tiny pieces flickering in and out of place? The truth is, we don't know, and that uncertainty sits at the heart of why space-time remains such a peculiar challenge. Another part of the mystery comes from the way space-time affects motion. When you're walking, you don't think about being guided by a curved landscape you can't see. You simply feel solid ground under your feet and move in whatever direction you choose. But everything you do, from the path you take to the time it takes you to get somewhere, is shaped by the curvature of space-time around Earth. If Earth were more massive, time here would run slower. Distances would subtly change. Your steps would cover different lengths depending on how strong the gravitational field was. You wouldn't feel any of that directly. It would all happen behind the scenes. That's why physicists often say gravity isn't something you feel. You only feel the effort required to stop yourself from falling deeper into a curved path. Our intuition, built from childhood as we watch objects fall and roll, doesn't prepare us for the idea that motion itself is the natural path through a curved geometry. If you toss something upward, you think gravity pulls it back down. But the deeper explanation is that space-time curves around Earth in such a way that any object left alone will follow a curved trajectory. The object isn't forced downward, it simply moves along the shape of the space-time it's travelling through, and the shape of that space-time curves back toward Earth. When you see it that way, gravity becomes something much subtler than a pull. It becomes a property of the environment itself, and the entire universe is filled with this environment. To understand why this is so hard for people to grasp, imagine trying to walk in a perfectly dark room. The floor might slope gently, but if you can't see the slope, you wouldn't think the floor is changing. You would simply feel yourself moving in unusual ways and assume it was your own doing. That's how motion works in a curved space-time. We can't see the curvature directly. We only see the results of moving through it. So the universe we experience is partly shaped by something invisible that never calls attention to itself, and that makes it hard for our intuition to catch up. Even describing space-time mathematically is challenging. Einstein's equations, which explain how curvature arises from mass and energy, are notoriously complex. They work, but they work in a way that's hard to translate into everyday thinking. The equations describe relationships between distances and times, but they do so using tensors, tools that can handle complicated interwoven directions. These tools allow physicists to calculate the geometry of space-time in any situation, whether near a star or inside a galaxy cluster. But knowing how to calculate something is not the same as understanding it intuitively. If someone asked why this geometry takes the shape it does, or what it's made from, or why mass curves space-time at all, those questions are still open. The equations give the how, but not the why. Part of what makes this even stranger is that space-time doesn't just respond to mass, it responds to energy, pressure, movement, and even the absence of matter. Empty space has properties. It isn't a blank background. It can expand, stretch, and change even in places where there's nothing at all. The expansion of the universe is a clear example. Galaxies aren't drifting away because they're moving through space like boats on water. They're drifting apart because space-time itself is stretching, carrying them with it. That stretching doesn't need engines, forces, or winds. It's a built-in behavior of space-time, which means the very emptiness between galaxies has structure and dynamics, even though it looks empty to us. And this leads to another difficulty. When we try to study something that doesn't behave like a substance and doesn't act like a force, we run into limitations. If you push on air, it moves. If you heat metal, it expands. If you stretch a rubber band, you can feel the resistance. But if you ask what happens when you stretch space-time, the answer is not so straightforward. Space-time doesn't resist. It doesn't exert a pressure that can be measured in the usual sense. It doesn't have a texture. It simply changes, and the only sign of that change is the movement of whatever sits inside it. This lack of direct interaction means we're always studying space-time indirectly, through the behavior of things moving through it. And studying something only through its effects is like trying to understand wind by watching leaves move. You see the consequences, but not the thing itself. Something else that complicates the picture is that space-time is dynamic. It's not a fixed container. It evolves, ripples, and interacts with the universe it holds. When two black holes merge, the collision sends ripples outward, stretching and compressing space as the waves move. We've detected these waves, and the measurements match what general relativity predicts. But observing something doesn't immediately make it intuitive. The idea that space itself can vibrate like this is very different from anything we experience directly. When a wave passes through Earth, changing distances by tiny amounts, Nothing feels different. Your body doesn't sway. Your bed doesn't move. Yet the wave is real, altering the geometry around you for a brief moment. Trying to understand something you can't feel or see, yet is always present and active, is naturally hard. We aren't built to sense these things. Evolution didn't require us to understand cosmic scale geometry in order to survive. Our senses developed only to help us interact with surfaces, shapes, and distances in the world immediately around us. So when the universe turns out to operate on principles far beyond what we're equipped to detect, we end up needing mathematics, instruments, and imagination to fill the gap. Another challenge comes from the fact that space-time contains both space and time brings its own complications. Time is something we experience, but we don't experience it in a consistent way. It stretches and compresses depending on what we're doing. The fact that space-time weaves this uneven sense of time together with the geometry of the universe creates a structure that is difficult to visualize. If space were the only part, we could picture it as a shape. But when time becomes part of the structure, shape becomes an incomplete description. The geometry now changes depending on motion, perspective, and gravity. The result is a landscape where time can move differently for different people in different places, making the structure feel less like a fabric and more like a living map that adjusts itself for every observer. And all of this circles back to why we say space-time holds everything together. It doesn't hold things the way glue does, or the way a web traps whatever lands on it. Instead, it holds everything by setting the rules for how things move and how events unfold. The shape of space-time determines the paths that objects follow. The way time flows determines the order in which events happen. Together they make the universe coherent, even if the coherence is hidden beneath layers of complexity. What makes this structure so difficult to fully grasp is that we're used to thinking of things as either places we move through or clocks that measure change. Space-time is both at once, a place and a system, a map and a timeline, a geometry and a rhythm. Trying to blend those ideas into one picture is not something our minds naturally do. It becomes easier to see why this structure feels so mysterious. It's everywhere, it shapes everything, and yet it never directly reveals itself. And that quiet hiddenness is part of what makes exploring it feel like wandering through a puzzle that stretches out just beyond the edge of what our thoughts can comfortably grasp. It's always interesting to think about how certain ideas in science become familiar to us almost immediately, while others seem to drift just out of reach no matter how many times we hear them explained. Einstein's picture of space-time is one of those slippery ideas. You can hear it described dozens of ways, listen to countless videos about it, and still come away with a feeling that something didn't quite click. It's not a failure of imagination or intelligence, it's something built into the idea itself. Einstein reshaped the foundations of how we view the universe, but he did it in a way that doesn't line up with how our senses process the world. So even though the theory has been around for more than a century, most people still find it strange. And honestly, that reaction is natural. Part of the reason Einstein's idea feels so unfamiliar is that it asks us to rethink things we've been certain about since childhood. We grow up trusting that space is just a big, empty area where things sit, and time is a steady flow that moves forward, whether we pay attention to it or not. These ideas come from everyday experience, not textbooks. You don't need to study physics to know that if you drop something, it falls straight down, or that if you start watching a movie at 8 o'clock, the next hour passes at the same rhythm it always does. Then suddenly Einstein comes along saying those simple assumptions aren't accurate, space isn't empty, time isn't steady, gravity isn't a force pulling objects downward, and both space and time can stretch, bend, and warp depending on motion and mass. No matter how calmly someone explains it, that's a lot for the mind to absorb. Another challenge is that much of Einstein's theory doesn't align with the way humans evolved to interact with the world. Think about how your brain judges distances and times. When you walk across a room, your sense of space is straightforward. When you wait for something to happen, your sense of time is linear. But Einstein describes a world where space and time are interconnected and influenced by factors our senses can't detect. Nothing in our daily routine suggests that time runs differently at different heights, or that space curves in the presence of mass. So when we hear these ideas, our first instinct is to try to fit them into the mental framework we already have. Unfortunately, the old framework doesn't match the new one. and the mismatch makes Einstein's ideas feel like they belong to another reality altogether. Even something as simple as the speed of a light being constant in every situation is counterintuitive. If you throw a ball while standing still, it moves at one speed. If you throw it while running forward, it moves faster relative to someone watching. That's easy to grasp. But Einstein shows that light doesn't behave this way. No matter how fast you move, the speed of light remains exactly the same. And because the speed of light refuses to change, something else must change instead. That something ends up being space and time. Distances compress or stretch. Durations slow down or speed up. These adjustments keep the speed of light fixed, even though nothing else in our experience behaves like that. Trying to picture this leads to one of the first mental roadblocks. Most of the things we understand are based on patterns we've seen. When you stack blocks, you learn about solidity. When you pour water, you learn about flow. When you spin around too fast and feel dizzy, you learn about motion. Einstein's theory deals with conditions that our senses never directly encounter. We don't move at speeds close to light. We don't live around objects massive enough to make space-time curve in obvious ways. We don't experience time dilation or length contraction in daily life. So the theory has almost nothing in common with the patterns our brains rely on. Another reason Einstein's idea still feels unfamiliar is that the explanations we often hear are simplified metaphors. They are helpful but incomplete. You hear people talk about the fabric of space-time, or a rubber sheet with heavy balls placed on it, or clocks ticking differently depending on where they are. These comparisons can give a sense of what's happening, but they don't fully capture the deeper ideas. They can even make the concepts feel more confusing because they resemble things we understand, yet they behave differently. When something looks familiar but doesn't follow familiar rules, the brain doesn't quite know how to categorize it. Take the idea that time can slow down depending on how fast you move or how close you are to a massive object. You can listen to the explanation and nod along, but unless you've experienced it, it won't feel intuitive. And since none of us have traveled at speeds close to the speed of light or lived beside a black hole, our understanding remains theoretical. We can measure these effects using atomic clocks and satellites. We can prove they're real with experiments. But having evidence is different from having intuition. You can believe something fully without feeling it instinctively. Einstein's idea also challenges one of our strongest assumptions, that there is a universal now. It's comforting to think that at this very moment, everyone everywhere is experiencing the same point in time. We picture the world as synchronized, even though we know people live in different time zones. Einstein's theory breaks this assumption. What counts as now depends on your motion. Two people moving relative to each other can disagree about whether events happened at the same moment, not because one of them is wrong, but because simultaneity isn't absolute. This idea alone is enough to make people pause because it disrupts something very basic about how we perceive our place in the world. Another strange thing about Einstein's picture is that it doesn't tell you why space-time behaves the way it does. The equations show how mass and energy influence the curvature of space-time, and how that curvature influences motion. But the underlying mechanism is still unclear. It's like having a map that accurately shows the roads and intersections but doesn't tell you who built them, or why they take those specific shapes. You can describe space-time as geometry, but the question of what exactly is being curved remains open. That gap in understanding makes the theory feel incomplete on a fundamental level, even though it works perfectly for predictions. One more reason the idea feels unfamiliar is that the pictures used to visualize space-time curvature tend to be two-dimensional, even though the real structure is four-dimensional. When you see a diagram with a grid being pulled downward around a sphere, that grid is a stand-in for something much more complex. We look at the diagram and instinctively try to interpret it as we would interpret a drawing of hills or valleys. But the curve in space-time isn't a curve in a physical direction, it's a curve in the geometry itself. Our mind tries to imagine bending something without bending it into anything else, and that's not something we have prior experience with. The visualization is useful for calculating or demonstrating a principle, but it doesn't create true understanding. Another element that adds to the difficulty is that Einstein removed the need for forces in his explanation of gravity. Forces are easier to picture. If you push something, it moves. If you drop something, gravity pulls it downward. But Einstein says objects move along natural paths in curved space-time, and the sensation of gravity is really the sensation of resisting that natural motion.